This is lecture 2 for module 6 in the book Problem-Solving Guide for Electromagnetism and Optics. Here we cover a couple of short topics: resistor breakdown and the power generated in a resistor. Breakdown current is where we'll start. When we had capacitors, we talked about a breakdown voltage, the maximum voltage across a capacitor before the charge can't stand it anymore and leaps across. Sparks across the capacitor. It leaps across the gap. It fries the capacitor. Resistors can burn out if the current through them gets too high. You try to push too much resistance, the thing will start to smoke, start to smell. I smell something burning. That's the resistor. The key, when you look at a circuit and figure out what the breakdown current is, look at the vulnerable element. Identify which one's going to blow out first. With capacitors, you said which one has the highest voltage drop. That's the one that's going to go. With resistors, it's the one that gets the most current. So let's consider a circuit above. Each resistor is rated for 2 amps. They can have a maximum current of 2 amps. There's a variable power supply, and I start cranking it up. Pretty soon, one of them is going to start to smoke. Which one is it? It's the one that gets the most current. If they're in parallel, they're going to have the same voltage drop. The 30 ohm resistor has a lower resistance. It's going to get more current for the same voltage, so the 30 ohm is going first. It'll start smoking when it has the current, the burnout current, which is 2 amps. It's going to get to 2 amps. V is equal to IR when the voltage across it gets to 60 volts. And that is across the power supply. So when this thing gets to 60 volts, the 30 ohm is going to start to smoke. It's going to fail. There's only going to be 1 amp going through that guy. It's got twice the resistance. It's going to have half the current. Now let's put another resistor in the series. Like that. I added a third one over here on the right side. Which one is vulnerable? Which one's going first? Which one of those 3 resistors is going to get to 2 amps first? I'm going to take this power supply, start at 0, turn the knob, turn the knob, turn the knob. Oh, I smell something. Which one is it? Think about it. Well, the 100 ohm resistor gets all the current. The current splits up there. These 2 guys are going to have less current than that one. Has to be. The current through this one is the sum of these 2. So it's the 100 ohm resistor that's vulnerable. So now I have to calculate the voltage of the power supply when 2 amps is going through here. There's a couple of ways to do that. We can get the equivalent resistance of the whole circuit. The 60 and the 30 in parallel gives a 20. You should do it. A 20 and a 100 in series gives 120. So the current through this resistor is the current through the battery. So we can calculate the voltage of the battery. It's 120 ohms. And that is times 2 amps, which is the current, 240 volts. And this is to get the 240 volts. The equivalent resistance of the circuit is 120 ohms, and the current through this 100 ohm resistor is the current through the battery. So when this gets to 240 volts, that's going to have 2 amps going through it, and it's going to start to smoke. The final concept is power. How much heat is generated in a resistor? How much thermal energy is generated? So let's consider a simple circuit again: battery and a resistor. The voltage across the resistor is the voltage of the battery, and voltage is joules per coulomb. The electrons that are going through the resistor experience a voltage drop of V joules per coulomb. All of this appears as heat. So before we talked about a charge going across the gap of a capacitor and increasing in kinetic energy. It's a free fall. It's going through a vacuum. These electrons going through the resistor are just pounding against the lattice, and as soon as they get up to some speed, they're going to bash into the lattice and make vibrations, heat, thermal energy. So they come out the same speed as they went in, and all of it's generated as heat. So we have some Q going across. The energy, the total energy, is the Q going across times the voltage drop. That's joules per coulomb. We want to know what the rate is. To get the rate, we got to divide by the time. So the energy is Q delta V, divided by the time, that's joules per second, that's the power. The units of P are, there's the coulombs from the Q, the seconds from the time, and a volt is a joule per coulomb. That gives us joules per second, and that's a watt. The expression Q over T in the equation is that's just the current, charge per time. So the power is I. The power generated by the resistor is I, the current through the resistor, times the voltage drop across the resistor. This should make sense, right? You're gaining thermal energy, a charge is going across a potential drop. Joules per coulomb is the voltage. Coulombs per second is the current. That's joules per coulomb. Joules per second, which is a watt. So electric stoves, you want to get that thing hot as fast as possible. That's like 3,000 watts of power. It's directly proportional to the current and the voltage drop across it. I delta V. If you want to make some tea, heat up your water, you use something like that, dip it in water, plug it in, it'll generate heat. These are like 300 watts. Any kind of electric heater, current generating heat, for example, rear defroster on your car. The final note is that we can use V is equal to IR to express the power differently. It can be convenient to express the power a different way. So power is I delta V, but we can use V is equal to IR and substitute in IR for V, and that makes it I squared R. We can also substitute out the current and get the voltage squared divided by the resistance. That's Module 6. Get to work.